Hello, good afternoon learners. This is Monica Jain from Sri Rama College of Engineering. Today we will commence our part of hydrology. Okay, so in water resource engineering and hydrology, the very first concept or very first topic is related with the hydrologic cycle. Now, hydrologic cycle or hydraulic cycle is also termed as your water cycle, and it is the normal water recycling from the earth. Due to the solar radiation, water evaporates generally from sea, lakes, etc. Water also evaporates from plant leaves through the mechanism of transpiration. Now, water never leaves the earth, but it constantly being cycled through the atmosphere, ocean, land, and this process is termed as your water cycle. And it is driven by the solar radiation or the energy given by the sun. Now, hydrologic cycle is basically the sum of your all processes in which water moves from the land and ocean or the surface ocean to the atmosphere and back in the form of precipitation. The hydrologic cycle will totally depends on various factors and equally affect your ocean as well as the land surfaces. Now, as the water evaporates from the plant leaves and it is termed as a transpiration, as the steam rises into the atmosphere, it is being cooled, then condensed, and it will return back to your land and in the term of precipitation. Again, this precipitation will fall on the surface of earth or fall on the earth as a water droplet and create the stream of water that results into the flow of water into the lakes as well as in the river. A part of your water will precipitate and penetrate into the ground and moves downward through the various aquifers or various galleries, and finally again a part of surface of water will leads to add to the sea. During this whole journey, during this whole uh, cycle, water is converted in all phases like gas, liquid as well as solid. Your water will also always change from state between liquid, vapor as well as ice with the stages or with the processes happening into the environment as well as on the surface, and it is the continuous process. So this process is happening because of the atmospheric change in temperature as well as the energy balance from the sun. The warming of climate system is again a unequal process. If it is a cooler one, then your hydrologic cycle will move accordingly, and if your weather is hotter one, then again your hydrologic cycle will move accordingly. Now, there are various components of the hydrologic cycle as we have seen, like evaporation, evapotranspiration, condensation, precipitation, interception, infiltration, runoff, and the surface storage. Okay. Now we'll see one by one that your first process is your evaporation. Now, what is evaporation? It is the one of the major process into your hydrologic cycle, and evaporation is nothing but the transfer of water from the surface of the earth to the atmosphere. By evaporation, your water is actually converting its liquid state to the gaseous or vaporous state. This transfer occurs when your some molecules in the water has attained kinetic energy and they moves into the atmosphere. Now, this evaporation will happen because of few factors, and those factors are your temperature, humidity, the speed of the air or wind speed, and the energy of the environment or atmosphere, that is your sun energy, solar radiation. Now you cannot measure the quantity of direct evaporation at all the points, but it is not possible that you can measure your evaporation at all the points, but there are few methods by which we can measure the quantity of evaporation. Again, your principal source of water vapor is ocean, but evaporation also occurs from soil, snow, drizzles, ice, and etc. When your transition is happening from what a vapor state to liquid state, it will called as your condensation. Okay, after evaporation there is a process of condensation, and condensation is nothing but the state change between the from liquid to the vaporous state. Condensation is takes place from the air contains more water vapor than it can receive from the free water surface through evaporation. Now, this condition occurs as the consequences of either cooling or mixing of air masses of different temperature. By condensation, your water vapor in the atmosphere is released in the form of precipitation. Precipitation that falls to your earth is divided into the few main streams. Some will be returned to the atmosphere again by means of evaporation. Then some part of the precipitation will be intercepted by the vegetation and then again evaporated from the surface of leaves or surface of green bodies as well as from the surface of earth. Then again some part of the soil will get infiltrated into your earth surface and remaining part will flow as a direct runoff. Some of the infiltrate precipitation again leads to add to your water table and it will termed as a groundwater runoff. Direct measurement of your groundwater runoff is made by strain gauges, and we have to plot the graphs that are termed as a hydrographs. We will learn it about later. Most of the groundwater is derived from your precipitation and that will percolate into the soil. Groundwater flow rate compared with those of surface water are very slow and the variables. Okay, so next process in your hydrologic cycle is transpiration. What is transpiration? Transpiration is a biological process in which your water is lost in the form of water vapor from the aerial parts of the plant. Evaporation is nothing but the what is evaporation? Evaporation is process in which your water is converting its state from liquid to the vaporous state but from the surface of earth. Therein your transpiration is the process in which your water is lost in the form of water vapor from the surface of the plants or from the green bodies. So transpiration occurs when plant takes in water through the roots and releases it through the leaves, a process that can clean water by removing contaminants and the pollutants. Okay, so there are different types of transpiration. Transpiration in plants will occur as water absorbed by the roots, then water will travel through the plant roots up to the heads or up to the leaves, and then water vapor lost will happen from the leaf from the pores of the leaf and it will evaporate into the atmosphere. So this process will termed as your transpiration. Now there are three types of transpiration: stomatal transpiration, then lenticular transpiration and cuticular transpiration. Now these terms are defined on the basis of parts of the green bodies from where the transpiration or from where your evaporation from the green body is happening. Okay. There are various factors on which your transpiration process depend, and those factors are the how your orientation of leaf is, where your leaf is actually orienting, then the water state, so level of status of water into the your plant, then structural configuration of leaf and number of stomata present into your leaf structures. Then again there are few environmental factors like humidity, temperature, light and air. Humidity, more will be the humidity, lesser will be the transpiration. Then temperature, higher will be the temperature and lower the humidity, then lower will be the transpiration. But higher will be the humidity, lower will be the temperature, then more will be the transpiration. Then light, as the stomatas are open during the daytime and close into the dark time. Presence of light is directly proportional to the rate of transpiration. Okay, so the stomatas are open during the daytime, so there will be more transpiration into the day, in the daytime. Then availability of water, transportation rate is again directly proportional to the absorption of water by the roots of the soil. More will be absorption of water, more will be the transpiration. Now there are few significance of transpiration in plants. Transpiration helps in the condensation of water and mineral of the different plants parts. Then again it maintains the environmental humidity. Then it gives the cooling effect to the trees due to the evaporation of water from its leaves. Then there is process of condensation. The condensation happens when your liquid or your gaseous droplets or gaseous vapor pressure are converting into the liquid state, then that process is termed as condensation. Then there is a precipitation. Precipitation is when water in the clouds gets back in the form of water, falls back in the form of water to the earth. This is called as a precipitation. The last term is your runoff. So when your rain falls on the land, some of the water is absorbed into the ground, forming packets of water called groundwater. That is the amount of water which will percolate deep into the ground and adds to the groundwater table. That is termed as your groundwater. And most of the groundwater frequently return to the ocean from the surface only. Okay, so the other precipitation runs directly into the streams. So that part of the water which will not get percolate into the groundwater and stay on the surface of earth will termed as your runoff. Okay, so basically, uh, the process of hydrologic cycle is a continuous process which will involve various stages like evaporation, transpiration, condensation, precipitation, then surface storage and runoff. By these all steps or these all processes are continuous, happening simultaneously or one after the other. Then there is evapotranspiration. Now evapotranspiration, as name itself is suggesting, it is combination of two processes, that is evaporation and transpiration. Now evaporation is nothing but loss of water from the soil surface, and transpiration is nothing but the loss of water from the plant surface. Okay, so evapotranspiration is the combination of both the processes, that is the total amount of loss of water from surface as well as from the plant surface. Now, what is basic difference between the transpiration and evaporation? Transpiration is a physiological process and evaporation is a physical process. Now, see, transpiration is a continuous process or evaporation is a continuous process. Transpiration is a continuous process because evaporation will happen into the daytime. Okay, it needs the solar energy, but transpiration can happen in daytime as well as into the night time also. Again, in transpiration, the loss of water is from the free surface of cells, and evaporation, loss of water will happen from the free surface of water. Transpiration is regulated process, it is a continuous process, and evaporation is non-regulated or discontinuous process. Then it is comparatively slow process, but evaporation is quite faster process. Then how the anatomy of your plant cell is and how the configuration of plant cell is, it depends on that. Transpiration depends on that, but evaporation has no such influence. If there is an open surface, there is a water present into that surface, then your evaporation process can happen provided with the sunlight or the solar radiation. And there are few factors which will affect your transpiration or evapotranspiration process, that is air temperature, humidity, movement of water. More will be the temperature, higher will be the evapotranspiration. Then more will be the humidity, lesser will be the evapotranspiration. Then there are two basic terms related with the evapotranspiration, that is potential evapotranspiration and actual evapotranspiration. Now, evapotranspiration, potential evapotranspiration is a measure of ability of atmosphere to remove water from the surface through the process of evaporation and transpiration, assuming no control on water supply. And actual evapotranspiration is the quantity of water that is actually removed from the surface due to the process of evaporation and transpiration. So potential evaporation is the quantity of evaporation or quantity of water that is actually evaporating from the surface as well as from the green bodies. But actual evapotranspiration is the actual quantity of evapor actual quantity of water that is being evaporated from the surface as well as from the grain bodies. So basic difference between these two quantities is actual evapotranspiration is the actual quantity, but potential evapotranspiration is the total capacity of the atmosphere or the environment, that how much quantity of water can be evaporated or can be accumulated into the atmosphere. If supposed to be yesterday there was a water incident, okay, rainfall was there. So what will happen because of that? There will be increase in the humidity into the atmosphere. So on the next day, the amount of evaporation as well as transpiration, that is evapotranspiration, happens from that land will be termed as your actual evapotranspiration. Okay, because now your environment is quite saturated, it is quite wet, but the total quantity of evaporation that can happen into that culture is termed as your potential evapotranspiration. Then there are few methods, empirical as well as practical methods, experimental methods by which we can find out the evapotranspiration. So lasimeter is a device which will useful to measure the evapotranspiration. The amount of actual evapotranspiration is released by plant from crops as well as trees. So actual evapotranspiration has been calculated by the decimeter. So there is one formula by which you can find out the actual evapotranspiration quantity, that is the ET value, that is P plus I minus D plus S, where ET is your evapotranspiration, P is precipitation, I is irrigation value, D is excess water. Okay, excess water is nothing but your runoff water, and S is the increase or decrease in the storage of soil. The next fundamental related with your hydrology is the infiltration. So infiltration is the process by which your water on the ground surface enters the soil. It is the process in which your water on the ground enters the soil, or it will infiltrate into the soil. Infiltration, then there is one more capacity, that is one more term related with infiltration is your infiltration capacity. Infiltration capacity is nothing but maximum amount of water that can be infiltrate into the soil strata or into the earth surface. It is measured in meters per day or length per unit time. There is one more term, that is the percolation. So the infiltrate water first meet the soil moisture deficiency. Okay. If any and excess water moves vertically downward to reach the groundwater table, this vertical movement is called as a percolation. So when your surface of water, your soil is dry soil, then what will happen? Amount of water will be required to saturate the water requirement of your soil strata, and then if some amount of water will remain there, then that water will get added into the groundwater table, and that water will get percolated beyond the soil depth. So that amount of water will be termed as your percolated water, and that process is termed as your percolation. Then infiltration capacity, it is the maximum rate or maximum capacity of the uh, soil by which your water can be absorbed, and it is denoted by the f small f. If your infiltration is greater than or equals to I, then your FA is equals to F. FA is nothing but your actual infiltration capacity, I is your rate of rainfall, and F is the infiltration capacity. Okay, so if your I is greater than or equals to small f, then it will be your your actual precipitation capacity will be equals to your infiltration capacity. It means there will be no percolation will occur. And if your I, that is rate of rainfall, is greater, lesser than your infiltration capacity, then what will happen in this case? FA is equals to I, that is actual infiltration capacity is equals to rate of rainfall. So in this case, if the saturation level will reach up to the maximum requirement of the soil, saturation of soil water requirement, then your water may percolate. Okay, so if your F is more, then your is dry soil, because F is nothing but your infiltration capacity. Okay, so if F is more, it means it is a dry soil, and if F is less, then it is the moist soil. Then there is one more term or one more quantity related with the infiltration and precipitation, that is a hydraulic conductivity. And hydraulic conductivity is the ability of a fluid to flow through a porous medium. It is determined by the size and shape of pore space in the medium and viscosity of the fluid. It is expressed as the volume of fluid that will move in unit time under the unit hydraulic gradient through a unit area measured perpendicular to the direction of flow. Now see, your infiltration process is the continuous only if there is a room available or the additional water into the soil surface. The available volume or the additional water in the soil depends on the porosity of your soil and the rate at which previously infiltrated water can move away from the surface through the soil. The maximum rate that water can enter the soil in a given condition is the infiltration capacity. When your water will arrive on the soil surface is less than the infiltration capacity. Sometimes we can also say that it is analyzed using hydrology, transport model, then mathematical model. Then again there are the runoff channels to predict the stream quantity or the water quantity into the stream. Then there are hydrological budget equations by which we can find out, or we can solve the simple equations or simple examples of the infiltration and the hydrologic cycle. Now, there are few factors by which your infiltration capacity depends, on which your infiltration capacity depends. That is slope of the land. More will be the slope, more will be the slope, lesser will be the infiltration, because water will try to get into the runoff. It will run under the into the gravitational force. That is why it will flow as a runoff water. Then degree of saturation, more will be the saturated water, lesser will be the infiltration. Then porosity, more porous is the soil, more will be the infiltration. Like soil, concrete, they are the more porous material as compared with the metallic materials. Okay, so there will be more infiltration rate into these materials. Then your next topic is hydrographs. Now, hydrographs are nothing but the plots which are plotted for the discharge and the time. So these are the graphs showing the rate of flow versus the time over a specific point in a river or other channel. Now, rate of flow is typically expressed in cubic meters or meter cube, and time is expressed in your seconds, either in minutes or hours. Okay, so it is a graph actually showing your total volume of water that is actually entering into the catchment, or you may say it will leave the catchment over a particular period of time. Now, hydrographs are used for design of sewerage, then specifically design of surface water, sewer pipelines, then water pipelines, etc. So there are few elements of this hydrograph. This is how the hydrographs look like. Okay, here see, there are few terminologies related with this hydrograph. First one is your discharge. Then there is one rising limb. This one from W to X. This limb is your rising limb. Then there is a peak discharge. This discharge is your peak discharge. Then there is a recession or a falling limb. This limb is termed as a recession or falling limb. Then there is a lag time. Lag time is the time from the first water enters or first peak rainfall to the peak discharge. This is termed as your lag time, and the time of peak. Time of peak is the total time from the first rainfall point to the peak discharge point. We have to read this graph from the left to right. Okay, and here you are given the precipitation. This is nothing but your discharge. It may be either in meter cube per second or in the mm of depth to the duration. Here your duration is given in the days. It may be also in hours, seconds, or minutes. So what is discharge? Discharge is nothing but the rate of flow passing through a specific location into a river, channel, or any water body. It is measured at a specific point where you have to plot your hydrograph. Then there is a rising limb. Rising limb of this hydrograph is also known as the concentration curve. Then there is a peak discharge. This point, peak discharge is the highest point or the highest discharge in the hydrograph. Then your rate of discharge is the greatest. Then there is a falling limb, or you may also call it as a recession limb. The recession limb extends from the peak flow rate and onwards. Okay, once your peak flow occurs, then there is a recession into the peak flow. Then there is a lag time. Lag time is the interval from the maximum rainfall to the peak discharge. Okay, from the maximum rainfall to the peak discharge. Then the peak to time, a time to peak, a time interval from start of the rainfall to the peak discharge. That is from here your rainfall start is from here to the peak discharge. This duration is your time to peak. Okay, so this is how the hydrograph look like. Now here see, there is the flow which will be common or which will always stay on the surface of earth, and this is nothing but your base flow. An amount of flow which is added or which is common. So this is the, if suppose I will try to draw a horizontal line from here to here. So what will get? I will get my zero discharge at some point. So to get zero discharge, I have to reduce the base flow from the ordinates of this hydrograph. Okay. There are so many types of hydrographs like storm hydrograph, flood hydrograph, annual hydrograph, then direct runoff hydrograph. Then one more basic term related with the hydrograph, a very important term is the unit hydrograph. Unit hydrograph is the amount of runoff resulting from the 1 centimeter of the rainfall excess. Okay. Now see, in hydrograph, you may plot any amount of discharge for the any amount of duration. But in unit hydrograph, you have to plot a graph of water for the 1 centimeter or 1 unit of rainfall excess. It is the essential tool for determining the direct runoff response to the rainfall. Once we know the unit hydrograph for any catchment, then you may go for the multiple hydrographs related with that. 2 centimeter of hydrograph, 4 centimeter of hydrograph. So once you must know the unit hydrograph, then you can plot the hydrograph related with the respective different depth of the catchment flows or the catchment rainfalls. There are few basic assumptions related with the unit hydrograph. The effective rainfall is uniformly distributed within its duration. Then again the effective rainfall is uniformly distributed over the whole drainage basin. Then the base duration of the direct runoff hydrograph due to an effective rainfall of unit duration is constant. Then the ordinate of DRX, that is direct runoff hydrograph, are directly proportional to the total amount of direct runoff of each hydrograph. For a given basin, the runoff hydrograph due to given period of rainfall reflects all the combined physical characteristics of basin, that is time variant. Here, two things are very important and two assumptions are very important. One assumption is we have to consider the uniform rainfall distribution. That is, the rainfall distribution over a catchment is uniform. And second one is it is time invariant. That is, for a given basin, your runoff hydrograph due to given period of rainfall reflects all the combined physical characteristics of the basin. That is, over the time, it is having same physical property for the rainfall, for the catchment, for the runoff, etc. Okay, so how we can draw hydrograph? Just go through it. Okay, so if you have to plot a hydrograph, it is a problem is given here. Just read out this problem and now in a typical 6-hour storm, 4 centimeter excess rainfall is occurring. The flow recorded in the catchment is shown below. Derive a unit hydrograph for 6-hour storm, assuming base flow as 100 cubic meter per second. Okay, you have to find out the unit hydrograph for 6 hours. Then unit hydrograph, that is 1 centimeter of the rainfall for 6-hour storm. Then a base flow is given as 100 meter cube per second. Okay. Now you are given with the two ordinates, that is a time is given and then hydrographs are given. Hydrograph quantity is given, discharge is given. Okay, first of all we have to find out the direct runoff hydrograph, that is DRH, and then you have to find out the unit hydrograph for the 6-hour duration. Okay. So we are given with this, that is the time duration. Then this is your unit hydrograph observed readings. These two columns are given to you. Now in third column, you have to reduce the base flow. So here your base flow is given as 100 cubic meter per second. Okay. So in third column, you have to reduce your base flow from the observed hydrograph reading. So 100 minus 100, 100 meter cube of base flow is given. So 100 minus 100, 0, 100 minus 100, 0, 300 minus 100, 200 and so on. So this is your direct runoff hydrograph. That is the amount of hydrograph that will flow on the surface, that is the direct runoff hydrograph, DRH. Okay. Then you have to find out the units of ordinates of hydrograph. Okay. Ordinates of hydrograph will be calculated as amount of direct runoff hydrograph divided by, you are given with the 4 centimeter 4 you are given with the yes 4 centimeter excess rainfall, that is the ordinates which you are given, they are for the 4 centimeter of the rainfall. Then you have to find out for 1 centimeter, then divide these ordinates to 4, you will get your ordinate for the unit hydrogram. Okay, so 200 divided by 4, 50, 600 divided by 4, 150. At the end, you may also plot a graph for time versus discharge, that is discharge on y-axis and time on the x-axis. So there are so many methods by which you can find out the quantities or to estimate the magnitude of the discharge. That is by rational methods, empirical methods. Unit hydrograph is one of the method and flood frequency studies. The next topic is your flood routing. Now, flood routing is a process or is a technique. It is useful in determining the flood hydrograph at a section of a river by utilizing the data of flood flow at one or more of the upstream section. If supposed to be you are having a hydrograph for the upstream side, or you may say for the downstream side, by using that flood hydrograph on any one section of the catchment, you can find out the hydrograph of the another section of the catchment, that is termed as a flood routing or the flood hydrograph. Now, in flood routing analysis, we have to determine the flow hydrograph at a given point on a watershed from the known hydrograph on the either upstream or the downstream side. So what will happen? There is an attenuation. It's supposed to be on the upstream side. The depth of hydrograph is high. So on the downstream side, there will be an attenuation. Attenuation is nothing but the reduction into the peak of that hydrograph will observe. So what is attenuation? Attenuation is the peak of the outflow hydrograph will be smaller than that of the inflow hydrograph. And this reduction into the peak of the hydrograph is termed as attenuation. So there are few methods for the flood routing, and those methods are your Muskingum method is there. In Muskingum method, we are given with the equation that S is equals to Kx plus 1 minus x into O. By using this equation, you can directly find out the flood discharge on the another point or on the downstream side of the catchment. Then there is reservoir routing method, there is dynamic method and modified plus method. Next topic is related with your reservoir capacity or reservoir storage. Now this is the schematic diagram of the reservoir storage. Now reservoir storage or reservoir capacity is divided into the number of zones. Okay, they will be based on the purpose for which your reservoir is actually will serve. This is giving the schematic of your reservoir. In the reservoir, we are having that storage zone. Then there is a storage requirements. So see here in this diagram, it is showing the different levels or the different zones related with the reservoir capacity. That is the full reservoir level, minimum reservoir level, dead storage level, and maximum water level. So dead storage level is the here see here it is the dead storage level. This level is your dead storage level. This level is your spillway crest level. Then this is your foundation level. This is the bed level of your storage. Okay, so that storage is basically provided below the level, there are no outlets. Then there is a full reservoir level. It is the level up to which you can attenuate the maximum amount of water or maximum flood storage can be provided up to the full reservoir level. Then minimum drawdown level is the level below which reservoir will not be the drawdown so as to maintain a minimum head required for the power projects. The maximum water level is the water level that is ever likely to be attended during the passage of design flood. Okay, this by which your water should not yet exceed that level. That is the maximum water level. Then there is live storage, dead storage, and out surcharge flood storage. Live storage is the storage available for the intended purpose between fully supply level and the invert level. Then dead storage is the total storage below the invert level of the lowest discharge outlet. Then flood storage is the requirement of water or the water level between full reservoir level and the maximum water level. Now here for solving the reservoir capacity, you may use the mass flow method. Mass flow method is the basically easiest method to solve the storage reservoir. Although it is the very simple and straightforward, few shortcomings are also there. Okay, then we will after storage capacity we will move to the groundwater hydrology. Now in groundwater hydrology, first we must understand about the groundwater. What is groundwater basically is now the total volume of water on our earth's surface is approximately 13.6 into 10 raised to power 8 kilometer cube, out of which 8.3 into 10 raised to power 6 is stored in the form of groundwater only, which is approximately 0.62% of the total water of the earth. Groundwater is again the water present beneath the earth surface, and groundwater is that water which is exit into the pore space and the fractures of your rocks and sediments beneath the unsaturated zone of soil, which can flow freely into the well, tunnels, and springs. That is the open spaces below the ground area. It depends on the following factors like porosity, saturation, permeability of soil, then how many aquifers are there into the soil structure and the storage capacity of this groundwater. So what will be the storage capacity of the groundwater? This will totally depends on the geological formations. These geological formations are divided into four basic types that are aquifers, aquitard, aquiflude and aquiflues. So these four terms or these four classification will be classified on two basic two basic terminologies, that is the water retention or the water holding capacity and water flowing capacity. Now, aquifer are the materials or the geological formations which can hold the water as well as from which water can flow. Okay, so they are having the holding capacity as well as the water flowing capacity. Then there are aquitards. Aquitards are the material which can which cannot hold the water, but water can flow out of the aquitards. Okay, so those are the materials or the formations will be termed as aquitard. Then next are the aquiclude. Aquiclude are the material which can hold your water, but water cannot pass from it, and there is no flow of water from the aquiclude material. Like lenses, दलदल हम जिसको बोलते हैं ना, दलदल में पानी होता है but we cannot extract that water. So water holding capacity is there but water cannot flow out of that. And there are aquifuse material. Aquifuse materials or the formations are like they even cannot hold the water as well as water cannot flow out of them. Okay, so aquifers are the material, they are having water holding as well as water flowing capacity. Aquitards are there which cannot hold the water but water may pass to the aquitard materials, and aquifluid can hold the water but water cannot flow through it, or you cannot extract water out of it. And aquifers are the material, they neither allows water to flow out of it nor to they hold waters. Okay, so aquifers are the material which have water as well as you can extract water out of it. Okay, so aquifers are layer of porous substrate that contains transmit groundwater because it has the water transfer capacity or water transfer capability. Then water can flow directly between the surface and the saturated zone of aquifer. The aquifer is unconfined. Now there are two types of aquifer. First one is a confined aquifer and another one is a unconfined type of aquifer. Here see, confined is nothing but a condition where your water layer is sandwiched or your formation is sandwiched between two different layers. Okay, it is packed from both the sides, then this condition is termed as a confined aquifer. Then there is one more aquifer that is unconfined aquifer, and unconfined aquifer is it will not be packed from both the sides. It may pack from one side and but it has the open surface on the another side. So that aquifer is termed as your unconfined aquifer. Now here see, this is the confined aquifer as it is sandwiched between the different layers on both the sides. Is it? Here we are having a water body, but this water body is actually sandwiched between the two different geological strata, and this is termed as a confined aquifer. But here on the surface, if there is an aquifer, that will be termed as a, if there is a water body, that body will be termed as an unconfined aquifer. This one, because it is confined from one end, but it is open to surface on the another end. Okay, so there are two types of aquifer, that is confined aquifer. Confined aquifers are also termed as your artesian and pressure aquifer, and they occur where groundwater is confined under pressure greater than the atmospheric by overlaying relative impermeable strata. Okay, so here it is the confined aquifer which is enclosed by the two impermeable strata. Then there are types of aquifers. We have discussed it, that is aquitard, aquiclude, and aquifuse. You see in this figure, this is aquiclude, aquiclude having a water, but we cannot extract that water. And there are aquifers. Aquifers can hold the water. Again, water can be extracted. Then there is again aquiclude. You cannot extract water out of that. Okay. Here this is the confinement. Confinement means a hard layer bed or a rock strata. Then there is a confined aquifer between two hard beds or two different hard stratas. So this is your confined aquifer, or this may also called as your artesian aquifer. Then here in this aquifer, the water is confined at the bottom only and it is free to atmosphere. So this is your unconfined aquifer or the water table aquifer. Unconfined aquifers will occur at the shallow depth from the surface of earth, wherein your confined aquifer will occur at the deepest depth from the surface of earth. So there are few factors or few terminologies related with aquifers are porosity, specific yield, specific retention, then coefficient of permeability, then storage capacity, transmissibility, and storage coefficient. So aquifer or the amount of water that can be extracted out of aquifer. Aquifers are nothing but your wells. Okay, these are termed as your artesian wells. So our well is the one of the type of unconfined aquifer because we have extracted your well out of the shallow depth. If your well is extracted up to the deeper depth, then this is also termed as your confined aquifer. Okay, so aquifers may be equivalent to your hydraulic wells, okay, or your open well. So the factor, one of the factor of the aquifer is the porosity. Then there is one more term that is the specific yield. Specific yield is the ratio of volume of water that drains from the groundwater storage due to attraction of gravity to the total volume of the saturated aquifer. Then there is a specific retention. Specific retention is the ratio of volume of water that cannot be drained out to the total volume of saturated aquifer. Okay, the water which cannot be taken out from the aquifer or from the soil strata, that is termed as a specific retention. Then permeability of soil. Permeability of the soil is the ability of water that can flow out of the pores or the voids of the surface. Then to find out the permeability, there is a coefficient of permeability. So coefficient of permeability can be found out by laboratory test or by the field test. There are so many methods by which one of the method which is uh, useful or which is likely to be used more is the Darcy's method. By Darcy's method, we get a formula to find out the coefficient of permeability, that is Q is equals to KAI, where I is nothing but your coefficient of permeability. Q is the discharge, sorry, Q is equals to KAI, where Q is your discharge, K is the coefficient of permeability, A is the cross sectional area, and I is the hydraulic gradient. Hydraulic gradient is the ratio of depth to length of the section, that is H by L. There will be direct question on the Darcy's law, that how one can find out the quantity of, or how you can find out the coefficient of permeability by using the Darcy's law or by using the Darcy's formula. So here it is given that Q is equals to KAI. I is nothing but a hydraulic gradient, that is depth per unit length. K is your coefficient of permeability, A is the cross sectional area, and Q is the amount of discharge. The coefficient of permeability of variation of the list of variation is given over here for different materials. The coefficient will be different. Then there are different field tests, that is the pumping out test. In pumping out test, one of the scientists named as Duput has given a theory which is given for the well hydraulics, that is also termed as well hydraulics. So the coefficient of permeability of the permeable layer can be determined by pumping from a well at a constant rate and observing the steady state water table in nearby observation wells. The steady state is established when the water levels in the test well and the observation well become constant. When water is pumped out from the well, the aquifer gets depleted of the water and the water table is lowered, resulting in a circular depression in the transpiratic surface. This is referred to as the down draw curve of the cone of the depression. Now there are so many governing equations for the radial flow in the aquifer. That is how your water will flow into the aquifer, into your well. So there are 2 to 3 derivations to find out the amount of discharge in confined aquifer and in unconfined aquifer. So observe this figure. In this figure, this this depression is nothing but your aquifer. Okay, below aquifer there is an aquiclude. Again there is an aquiclude, and here it is a aquifer. Aquifer is nothing but your well aquifer or artesian aquifer. Here you can see the cone of depression as water will get extracted from this well. So what will happen? There will be drop down into the water level of well, but in the surrounding level of water will be high. Okay, so here again the water level is up to that, but here you can see the cone of depression. Because of this is termed as your cone of depression, because we are extracting water from this well. Then this line, this horizontal line is termed as your initial potential line. Then this amount of water, the amount of water or the depth of aquifer is your termed as width of the aquifer or control volume. This is your dr. Here it is your hard strata, or you may also call it as aquiclude. And from here you will get your discharge, that is the pumping rate or the Q value. So this is how you can find out the discharge as well as the coefficient of permeability for the unconfined aquifer. Okay, so for the unconfined aquifer, the formula to find out the permeability coefficient or coefficient of permeability is 2.303 q divided by pi d1 minus d2 in bracket twice h minus d1 minus d2 into log to the base 10 r2 by r1. Then for confined aquifer, again we are having a derivation, and it the coefficient of permeability will be calculated as q divided by 2.7283 into h into d1 minus d2 into log to the base 10 r2 by r1. Now here see, in confined aquifer, this is the final formula for confined aquifer. But if it is mentioned that you are having steady radial flow, then your equation will be reduced to the q is equals to 2 pi r bk into dh by dm, where b is the width of aquifer, k is your coefficient of permeability, dh is the depth of well, and dr is the diameter of your well. Again, if steady radial flow in a well is confined aquifer, then there are few conditions you can directly use, that your depth of the aquifer will be equals to directly depth of the water, and your equation will reduce to this equation. We have seen these equations. Okay. And if supposed to be you are given with, you have to find out the discharge when your well is in confined aquifer, then this is the final formula where Q is in the meter cube per second. For our references, K will be in the permeability and HS can be in height, depth can be in meter or mm. Okay, here see uh, example is given in hydraulic conductivity of an artesian aquifer being pumped by a fully penetrating well. The aquifer is 100 meter thick and composed of medium sand. The steady state pumping rate is 1000 GPS. The drawdown at an observation well 50 feet away is 10 feet. In a second observation well, it is 500 feet. Okay, so two different depths are given, two different observation well diameters are given. So you will use this formula directly. That is this one 582 q log to the base 10 r2 by r1 divided by m into h2 minus h1. So here all values are given. M is nothing but the thickness of aquifer, which is your 100. Then H2 and H1 are again given. That is the depth of the drawdown wells. That is 10 as well as 1. Then R2 and R1 is given as the thickness, that is discharge 1000. So put all the values and you will get your coefficient of discharge as 586.7 GPD per feet square. Then again to find out discharge in unconfined aquifer, you are having an equation, a consolidated equation. There are so many types of equation. We can consolidate those equations according to the given data. Okay. So this can be one of the consolidated equation, that is 1055 q log to the base 10 r2 by r1 divided by h2 square minus h1 square. So in this problem, a 20-inch wall fully penetrating and unconfined aquifer of 100 feet depth. Two observation well diameters are given and pumped out well known to have the drawdowns of 23 and 21.5. Okay, respectively. If the flow is steady, Kf is given, find the discharge. So you are given with the two diameters, that is the 240 and 90. Then depths are given. One depth is 21.5. One depth is 21.5 away from that drawdown and total depth is your 100 feet. So 100 minus 21.5 you will get one depth and 100 minus 23 you will get another depth. Put all the values, you will get your discharge. That is your Q value. Now there are so many parameters related with your aquifers like transmissibility, then permeability. So we are having different methods to calculate the transmissibility, permeability, then retentions. Once you will know all the parameters, then you may go for the final analysis or final study of the aquifer. In this section, there can be question on the well hydraulics on either confined hydraulics or confined aquifer or on unconfined aquifer. Then there can be a question based on the Darcy's law. Okay, that is Q is equals to KA I or KA H by L. Then there can be a numerical question based on the evapotranspiration, that how evapotranspiration will be calculated. Then there can be a question related with the water budget equation. Okay, you may given with the inflow and outflow and you have to find out the, or you have to find out the either You have to apply water budget equation and you have to find out the different losses or the amount of water into the different categories which we have seen into the water cycle. Then there can be a question related with aquifer and aquipart, that a definition will be given to, and which type of aquifer is this. This may be a question. Then uh, there can be a question related with the hydrograph. A data will be given to you and you have to write, you have to draw down either a direct runoff hydrograph or a unit hydrograph. Generally, a question of unit hydrograph is there into the competitive examinations. Okay, thank you.